more important are what we call the angle sum and angle difference identities. So here's the idea or the geometry between them. It's not completely obvious. It's a little bit tricky. Let me just show you where they come from. So if I have some angle alpha here, so let's remember that angle, and then I'm going to turn backwards some different amount. So I'm going to go back some amount minus beta. Okay, and I'm also going to go from alpha, I'm going to add the same amount beta but turn in the forward direction, so have some positive value. So let's see, how far would that get me? Probably about over to here somewhere if I were to add beta to alpha, so that this whole angle is alpha plus beta. Here's the observation. If you look at the distance from here to here and compare it to the distance from here to here, those distances have to be the same because it's the same amount of arc length on the circle, right? So this is a total distance of alpha and beta together, and so is this, right? Alpha and beta. So these two lengths have to be the same. Now we could actually find the coordinates of these points and then use the distance formula to find what those two lengths are and set them equal to each other. So the coordinates of this point involve alpha plus beta, because the horizontal component would be the cosine of alpha plus beta, and the vertical component would be the sine of alpha plus beta. So that's this location right here. Of course, this location is at 1, 0, and this location here, let's see, the horizontal component would be the cosine of alpha, and the vertical component would be the sine of alpha. And what about down here? The horizontal component would be the cosine of minus beta, and the vertical component would be the sine of minus beta. Now before I go any further, you should notice something about the cosine. Whether you turn the angle forward or backward, the horizontal component is the same if it's the same angle. So the cosine of negative beta is the same as the cosine of beta. On the other hand, though, if you turn forward, the sign is positive, right? But turning backwards, the sign is negative. That means that the sign of negative beta is the opposite of the sign of beta. Okay, this observation just says that cosine is an even function. It absorbs the negative, while sine is an odd function. It can pass the negative through. Can't pass other things through, but it can pass that negative through. Okay, let's go ahead and set up those two distances. So the distance from here to here, remember the distance formula says you take the square root of the square of the differences. So we have cosine alpha plus beta minus 1 squared plus sine alpha plus beta minus 0 squared. So sine squared alpha plus beta. Then that distance has to be the same as this distance, and this distance would be the square root of, let's see, we have cosine alpha minus cosine beta. Alpha minus cosine beta squared plus the difference in the y-coordinates is sine alpha minus sine beta, so that would be sine alpha plus sine beta. The two negatives made a positive there. Okay, so if I square both sides of this equation, and if I square this out, I've got the cosine squared of alpha plus beta. If I multiply this polynomial out, this binomial, by itself, I'm actually going to get a minus 2 cosine alpha plus beta plus minus 1 is minus 1 will make 1 plus sine squared alpha plus beta. And over on this side, if I multiply this out, I'm going to get cosine squared alpha and then minus 2 cosine alpha cosine beta plus cosine squared beta plus, now multiply this out. The product of the first terms makes sine squared alpha. The outside terms plus the inside terms make 2 sine alpha sine beta, and then the last terms make sine squared beta. So notice now, anytime I have cosine squared and sine squared of the same angle, that equals 1. So for example, I have cosine squared of alpha plus beta and sine squared of alpha plus beta. That makes 1. This one plus that one make 2. So on the left we have 2 minus 2 cosine alpha plus beta equals, over here I have the cosine squared and the sine squared, both of alpha. That makes 1. Here I have the cosine squared of beta and the sine squared of beta, so that makes 1. So I've got here 1 plus 1 is 2. And the only things left are a minus 2 cosine alpha cosine beta and a plus 2 sine alpha sine beta. Okay, this is looking pretty messy, but stick with me. I'm going to copy this line onto the next slide. So we've got 2 minus 2 cosine alpha plus beta equals 2 minus 2 cosine alpha cosine beta plus 2 sine alpha sine beta. Well, first thing you notice is that there's a 2 on both sides. And then if we divide through by negative 2, negative 2 divided by negative 2 is 1, and 2 divided by negative 2 is negative 1. So we get this identity, which says that the cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Okay, that's really handy, this identity. So I don't expect you to memorize how to derive that from those two distances, although students often ask, where did that formula come from? And you can see that it does come from geometry, but it's not quite as obvious, say, as like the Pythagorean identities or the cofactor identities. But it's kind of nice to know where it comes from. But if you'll remember this, you also need to remember 3 more. If you replace the plus with minus, you could think of this as alpha plus negative beta, and just replace the betas with negative beta. You'll get this identity. Cosine absorbs the negative, so you still have cosine alpha, cosine beta, but the sine passes the negative through, so you get sine alpha, sine beta. And you could use the cofactor identities, once you have these, to show that the sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So I had a teacher that used to chant sine, cosine, cosine, sine, 3.14159. If you remember what that's for, maybe that's handy. The 3.14159, of course, is an approximation to pi. If you have a minus in this case, then you get the sine of alpha and the cosine of beta minus the cosine of alpha and the sine of beta. Okay, these 4 are critical. Now there's a more compact way of writing them. Sometimes we write the first 2 this way. If it's alpha plus or minus beta, you get cosine alpha cosine beta. But notice the signs get reversed. When it's plus, it's minus. When it's minus, it's plus. So I do an upside down plus minus to indicate that reversal. So sine alpha sine beta. And the last 2 can be written this way. Alpha, sine of alpha plus or minus beta is sine cosine. Here the signs are straight, right? When it's plus, it's plus. When it's minus for that sine one. We get cosine alpha sine beta. These are called the angle sum and angle difference identities, and they're pretty critical. I would say, of all the identities to memorize, knowing these 4, okay, which can be reduced to just 2 equations, right? And then this one, cosine squared plus sine squared equals 1, that'll get you a lot of places if you just know some tricks. So I would definitely have these, I could call them 5 identities memorized. So these are the key 5 to memorize. Mix those with a couple tricks, and you'll always have enough identities to get your problems done.